Hello, I'm Trishank, a fifth-year PhD student at the NYU Tandon School of Engineering, where I work with Professor Justin Capos on software update security. Today I'd like to present our work on Uptane, which aims to secure software updates for vehicles. Uptane is a collaborative effort between NYU, the University of Michigan Transport Research Institute, and the Southwest Research Institute. First, let me define the main challenge. Allow me to quickly dispatch some background before going further. A repository is a server that contains images and metadata. An image is the smallest unit of update. It is a self-contained archive of all code and data required for an ECU to function. A vehicle has many ECUs, and each ECU installs one image. The repository also contains metadata such as cryptographic hashes and file sizes about images or other metadata files. So, the premise is that software updates over the air is coming to vehicles, and there are many good reasons for doing so. An OEM can improve existing features, add new ones, and most importantly, fix software bugs without the cost traditionally associated with an expensive manual recall. Although software updates over the air offer these benefits and many more, we must be careful to do it properly. To see why, let us ask, what do all of these major tech companies and open source software organizations who have some of the best security teams in the world have in common? It's that their users have been attacked through the software update mechanism, some of them multiple times. This is commonly done by compromising the repository that serves software to users and inserting a malicious update. The security problem is not unique to tech companies and open source software organizations. OEMs would also need to operate repositories to serve software to vehicles. Now, we assume that attackers can control communications anywhere between the repository and ECUs. So there are many attacks that can happen in between, and our system addresses them. However, in this talk, we focus on the worst case where attackers have compromised the repository. And if so, that they can also compromise the key stored on the repository that are used to sign updates. When a compromise happens, the impact is huge. Attackers get to install malware on unsuspecting vehicles. When attackers exploited the software update mechanism to spread malware a few years ago in South Korea, government officials estimated that the attack had cost $750 million in economic damage. In the case of vehicles, the impact is far more serious because human lives are at stake. Repositories currently use solutions such as TLS or HSM, but they still get compromised and updates still get tampered with. Unfortunately, it is a question of when and not if a compromise ever happens. So the goal with our system is not to prevent repositories from being compromised. Rather, it's to limit its impact. That is, even if the repository is compromised, we want attackers to be able to compromise as few vehicles as possible. We want to build a system that makes it extremely difficult for attackers to get all the pieces needed for complete control. So let's see how two previous security systems, each with an opposite trade-off, perform with regard to this goal. In the first system, repositories use a single online key or a key kept on the repository to sign all metadata. Typically, this is done using a transport mechanism such as SSL or TLS to encrypt connections. This system protects ECUs from man-in-the-middle attacks between the repository and vehicles. It also allows on-demand customization of updates because the repository can instantly sign different updates for different vehicles. However, the system is not compromise resilient because vehicles cannot tell whether or not metadata at rest has been tampered with. So, simply using SSL or TLS does not solve this problem. All an attacker has to do to install malware on all vehicles is to compromise the single online key. This is true even if repositories use a hardware security module or HSM to store the online key. In the second system, repositories sign all metadata using a single offline key, or a key kept off the repository, for example, on a USB stick in a safe deposit box. Since the key is offline, attackers cannot sign new metadata, and so vehicles are protected. This system is compromise resilient, but now we have lost on-demand customization of vehicles. This system does not let an OEM install updates for vehicles depending on fresh information. The OEM cannot easily customize updates depending on which vehicle it is and what it has currently installed. For example, two vehicles of the same make and model may nevertheless install different updates because one is a military vehicle whereas the other one is a test vehicle. The OEM may wish to fully control what is installed in test vehicles, but allow the military to also control what is installed on their vehicles. For this reason, in practice, this system risks becoming the previous system. Thus, OEMs shouldn't use previous systems because they force choosing either on-demand customization of vehicles or compromise resilient. That is why we designed Uptane, a new security system that lets OEMs have both. We do this by using two repositories. On the supplier repository, offline keys are used to sign metadata about all available updates for all ECUs on all vehicles. This system provides compromise resilience, but not on-demand customization of vehicles. On the director repository, online keys are used to sign fresh metadata about which updates from the supplier repository should be installed on which ECUs on a vehicle. This repository provides on-demand customization of vehicles, but not compromise resilience. Using both repositories, Uptane is able to provide both on-demand customization of vehicles and compromise resilience. Before installing updates, a vehicle would ensure that the updates chosen by the director repository matches the updates available on the supplier repository. In this manner, an attacker cannot install malicious updates on ECUs without also having compromised offline keys. This system makes it extremely difficult for attackers to get all the pieces needed for complete control. Uptane uses 4 design principles to provide compromise resilience. More details are in the paper, but I will briefly describe them to give an idea of how our system works. First, different types of metadata are signed using different keys, so that the impact of a key compromise is minimized and does not necessarily affect the security of the whole system. Second, a minimum number of keys may be required to sign a metadata file, so that attackers must compromise this threshold number of keys in order to install malware. Third, since keys can be compromised, there are 2 ways to revoke keys. Keys can be revoked explicitly by publishing new keys to replace old ones. Alternatively, keys can be revoked implicitly by setting an expiration timestamp on a metadata file. Fourth, the risk of a key compromise can be minimized by using offline keys. By combining these design principles, Uptane provides an OEM with a great deal of flexibility in signing updates. On the supplier repository, an OEM may delegate the signing of images to their respective suppliers. Note that delegations are flexible and allow for a wide variety of arrangements. In this example, the OEM signs images on behalf of supplier A. However, it has delegated some images to supplier B. It has also delegated other images to supplier C, who, in turn, delegates them to developers D and E. The director repository is separate from the supplier repository. Suppliers sign metadata such as hashes about images, but they do not indicate which ECUs should install which images. The director repository signs precisely such metadata. Using this repository allows an OEM to control exactly which images are installed on which ECUs on which vehicles. This repository also allows OEMs to immediately blacklist, say, buggy versions of images that have been signed by suppliers. Using both the supply and director repositories, Uptane is able to provide both on-demand customization of vehicles and compromise resilience. Uptane gives OEMs great flexibility in controlling which images are installed on which ECUs and who signs for these images. Now we discuss how ECUs would verify Uptane metadata before installing images. First, we divide ECUs into two types. We do this chiefly because different ECUs have different computational capabilities. For example, an infotainment ECU may be able to check many more signatures than a seatbelt pretension ECU in the same amount of time. Thus, Uptane is designed to accommodate different ECUs with different security and cost requirements. A primary is a special ECU that downloads, verifies, and distributes metadata and images to secondaries. Secondaries are other ECUs that receive metadata and images from a primary. A secondary installs a new image only if it has been successfully verified against the signed metadata. There are two types of metadata verification depending on an ECU's security and cost requirements. Full verification requires an ECU to check whether metadata about updates chosen for installation by the director repository matches metadata about the same updates on the supplier repository. This is an application of the two-man rule. Two different sets of keys, offline and online, from two different repositories are required to sign off an image. Powerful ECUs such as infotainment ECUs should be able to easily perform full verification. In order to prevent security attacks on behalf of secondaries, primaries are designed to perform full verification. Partial verification requires an ECU to check only one signature on one metadata file from the director repository. This is so that even very weak ECUs should be able to check this one signature. During manufacture, an OEM will provide every ECU with its metadata and image. An image consists of two pieces: a bootloader which executes startup routines, and an application which runs the desired ECU functionality. When an ECU boots or reboots, the bootloader would perform either full or partial verification before transferring to the application. Uptane also uses several design features to detect or prevent certain security attacks. These design features are entirely optional, depending on an OEM's budget and security concerns. More details are in the paper. Given all of these security features, the difference between ECUs that perform full and partial verification is in how resilient they are against a repository compromise. When there are only man-in-the-middle attacks, but no key compromise, then attackers cannot cause both types of ECUs to fail to interoperate. When attackers have compromised the director repository, there are two possible cases. If attackers have not compromised primaries, then they can cause both types of ECUs to fail to interoperate. Nevertheless, they cannot install malicious updates because primaries always perform full verification on behalf of secondaries. However, if attackers have compromised primaries, then they can install malicious updates, but only on partial verification ECUs. Attackers cannot install malicious updates on full verification ECUs until at least the right supplies keys are also compromised. In summary, Uptane offers basic security guarantees for all ECUs and provides greater compromise resilience for ECUs that can afford it. Uptane requires relatively little effort for OEMs and its suppliers to deploy. There are only three types of changes needed to use Uptane. First, an OEM performs a one-time step to set up the director and supplier repositories. After that, the OEM is expected to periodically update information on these repositories. An OEM may also run a time server to help ECUs prevent or mitigate a certain attack, but this is optional and more details are on our paper. Second, the supplier may sign metadata about images hosted on the supplier repository, or the OEM may do so on its behalf. Third, the software on an ECU needs to be modified to perform either full or partial verification. An OEM would set up automated processes to run the director repository. Except for cases that require human intervention, these processes would run this repository. This repository would parse reports from vehicles about what is currently installed on them. Given this information, it would perform dependency resolution or computation about which images should be installed next on the vehicle. Then it would use online keys and the Uptane API to produce signed metadata about its images. An OEM would also maintain the supplier repository, which is used to publish images produced by suppliers. Unlike the director repository, the supplier repository is maintained by human administrators. Furthermore, all metadata on this repository is signed using offline keys, so that attackers cannot tamper with images undetected, even after a repository compromise. To further increase security, we recommend using a threshold of offline keys so that a single key compromise is insufficient to publish malicious images. Administrators would use Uptane command line tools to periodically, for example weekly or monthly, update metadata about available images. All a supplier has to do, if it opts into it, is to sign metadata about its images on the supplier repository. Alternatively, an OEM may sign these images on behalf of the supplier. Suppliers would use the Uptane command line tools to run a single command that will produce signed metadata. Suppliers should use offline keys to prevent attackers who compromise the infrastructure from being able to sign for malicious updates. They can also use delegations to control which members of his organization are allowed to sign for which images. Finally, the software on an ECU needs to be modified to perform either full or partial verification. Full verification should be used by safety-critical ECUs that should not be hacked. To further improve security, these ECUs can also use optional features, such as using additional storage space to be able to roll back to a previous working image. All other ECUs, especially those constrained by speed or memory, should perform partial verification. If ECUs cannot perform at least partial verification, then we highly recommend that these ECUs are not updated over the air. Let me finish the talk with how you can freely implement Uptane today. Uptane is open source software that can be freely used by anyone. It is governed by the MIT license, which means that you can use our code however you like. We have published an RFC-style implementation specification, which you can use to implement Uptane using whatever technology stack that you like. Our reference implementation uses Python for simplicity and clarity, which you may refer to for building your own implementation. We will also publish some deployment considerations that discuss how you can configure and use Uptane in different ways to meet your own requirements. Uptane is sponsored by grants from the Department of Homeland Security, and we are grateful for their support. We are pleased to say that Uptane has been well received in our workshops, where we invited major American OEMs and suppliers to give us feedback. In mid-October, we presented a demonstration of Uptane to various government and industry representatives. We hope to accomplish 3 tasks in the near future. First, we will invite independent researchers to perform a security review. This is following a best practice in the security community, where we solicit open feedback and improve that way. Second, we will test independent implementations of Uptane for standards compliance. Third, we are planning to submit Uptane to the SAE for standardization. We hope that you would also like to use Uptane. We would absolutely love to hear feedback from you, so please reach out to us in one of these various ways. Thank you very much for your time.